Hey everyone, so we're going to finish up talking about kinematics with the angular projectile motion stuff. Essentially in here, we're going to combine the two projectile motions, vertical projectile and horizontal projectile, into one conglomeration of projectile motion stuff. Uh, for the most part, the setup is pretty much the same thing. We end up having an initial velocity in both the x and y direction. So there will be an initial velocity in both sides. And one thing that we have to make sure we do is oftentimes they don't have the numbers split up for us, so we're going to have to split up ourselves. Now, we're going to start off making an XY chart just like with every other projectile. There are going to be three knowns for most of these problems. The acceleration in the X and Y will still be known as 0 and -10, respectively, and the initial position in the X direction will end up being 0 because, why not? That's what we're going to go with. Now, the one thing to keep in mind is that the speed they give us, they're usually going to tell us the speed and the angle it's being shot at. Now, that speed does not go into our XY chart because that is an angled speed. When we talk about the XY chart, we need to figure out how much of that speed is going in the X direction and how much of it is angled in the vertical direction. Because if we angle it if we are shooting something at 30 degrees, that's different than if we shot it at 45 degrees. Because in the 45 degrees, it's a little bit more vertical, and therefore more of its velocity is going to be vertical than the 30 degrees. So when we go to plug in the speed into the XY chart, we do not plug in the 30 meters per second they tell us. Instead, we have to do 30 sine 30, or whatever the speed times sine theta to find the vertical component, and we have to do cosine theta for the horizontal component. So if you recall, this is just finding the components of that velocity. Just to clarify, so we have the object being shot at some angle. In this case, it's going to be 30. We're told that this is at a 30-degree angle. So what we're doing is we're finding the x component using cosine and the y component of the right triangle using sine. So you could go through the whole SOHCAHTOA part, but honestly, it's just so much easier to memorize this, to remember this, that when you're trying to find the y component, it's always hypotenuse times sine, and the x is always hypotenuse times cosine. All right. The only time you have to be careful is I was going to say accidentally, but if they give you this angle up here, but they would never do it for this problem, for projectile problems. That's something that comes down later on. Sometimes they might give you vertical angles, and you just have to realize that you have to always you can only do this setup when you have horizontal angles. But again, for projectiles, not going to be a thing. All right. So for this one, like I said, the key thing to remember about the X direction is that it really only affects the range of the projectile. So if you're looking for things like time in the air, maximum height, that's Y direction stuff. A lot of times, the object, if it lands on the ground or wherever the same surface that it got launched from, the final position is going to be 0. Um, Otherwise, you know, you just put in whatever the final position they tell you is. This part, every now and then you might deal with what I call asymmetric projectiles, where either the starting point or the ending point is kind of off kiltered at a different location than the other point. So here, this is an example where it ends at a higher height. This is an example where it starts at a higher height. Honestly, nothing really changes. The only difference is that you haven't have either a new initial or final y value. The one thing to keep in mind though is that when you do the annoying x this time, uh, unlike with the horizontal projectiles, when you do annoying x here, you're going to end up with a quadratic equation. So be careful. It's not a super common problem, and there are ways to get around it. But just be aware of that. That when you see these problems, they will be they could end up being a pain to solve. However, if they give you enough information, you won't have this issue. All right. The key thing when you're dealing with angular projectiles is that the very first thing before you even start is to break up the velocities into x and y directions. Now, there are some times where they actually will give you the x and y directions. They might say that the horizontal component is blank and the vertical component is blank, in which case you won't have to do that extra legwork. But if they don't, if they just tell you it's at some angle, that the velocity is at an angle, then you have to break it up into its components before you can move on. So keep that in mind that we cannot deal with a problem and something being at an angle. We have to break it up into its components. And then once you get to that point, it's pretty much just acting like it's the vertical projectile stuff. You have to be careful of things like maximum height, time of flight, things like that. And then you treat them, as is the way you do those problems. All right. So here's the first question. Pause video, work stuff. I'm gonna go over in a second. All right. So they want us to sketch the graphs of the motion it moving in the x direction. Again, I like to start from the acceleration and go backwards. Once, as always, the acceleration is constant, but this is constant 0 specifically. So there is no acceleration in the x direction. And because the acceleration is 0, that means the slope of velocity is going to be 0. So uh, now I have to ask myself, is this going to be 0? Is this going to be positive? Is it going to be 0, or is it going to be negative? Well, just by definition, it's going to be positive. So it's going to be a constant line with a slope of 0. All right. Now, because this is a constant graph, this means the slope of this graph is constant. So that means we're going to be drawing a line. This is linear. Again, we have to figure out where the starting position is. That's going to be our first point. Just the way that we always set up our problems, we always say that the initial position in the x direction is going to be 0. So it starts here, and then does it go up or does it go down? Well, because this slope is constant because this graph is constant and positive, that means this slope is constant and positive. So this should be a linear line going upwards with a constant positive slope. Okay, and those are our 3 graphs. Okay. Here's the next one. Pause video, work self, and we'll go in a second. Okay. Once again, this is going to be a constant graph, but this time there is an acceleration in the y direction. So this is going to be constant at negative because the acceleration is always negative 10. So straight constant line here. Because this has a constant negative, because this is a constant negative graph, this has a slope that is constant and negative. So this is going to be a linear graph. In this problem, it's being shot from the ground, so it's got to go up. So it's going to start with some positive initial velocity, and then it's going to have a negative slope to it. So I'm just going to draw a line that goes down. And that makes sense because eventually it has to go to 0 and then it has to come down. So that's what this graph is saying. Now here, because this graph is linear and changing, this means that this has a changing slope. So the slope changes, which means that this is going to be a curved graph. Now it says that the projectile is initially shot from the ground. So the initial position is going to be 0 like it usually is. And then it's going to end up going to a new, oh wait, this is in the y direction. So you know what? Let me actually change this to be y because this is kind of confusing right now. So initially it's going to start from the ground and then it's going to end up landing back on the ground. So eventually it will end up reaching 0 again. So I'm putting those 2 points here. And I know it's curved. So the question is it going to be curved upwards or is it going to be curved downwards? Well, conceptually, it makes sense for it to be curved upwards. But if we look at this graph, this starts off positive. So this should start off with a positive slope. So that means it should start off going up. And then it goes to 0. So it should level off. And then this goes negative. So this graph goes down. There you go. So this is what the 3 graphs should look like. Here's the next question. Pause video, work stuff, and we'll go in a second. All right. They want us to figure out the total time of flight for this object. So they give us this information. So let's see. This is what my chart will end up looking like. So again, the very first thing before I even start making the chart is break this up into components. So we do 24.5 sine of 35 in order to find the y component, and 24.5 cosine of 35 degrees to find the x component. But once I have that, then it's pretty straightforward from here. They want the total time of flight. So what I can do is the annoying x equation, but this time I'm switching the x with y, just to keep in mind what column we're looking at. So we do that. We plug our numbers in, and then let's see, we end up getting the time to be 2.8 seconds. Then for the distance in the x direction, what we're going to do is the annoying x equation, this time, using x terms. So we're taking the 20.1, multiply it by the 2.8, and we end up getting 56.3. Uh, to find the maximum height, I'm going to have to be a little careful because right now, a lot of this information is assuming for the ball landing at the same height. So what I could do is only use the initial values and use them in the timeless equation, or I can do the annoying x equation, or maybe I should say annoying y equation, and then half this time since that's it would take 1.4 to go up and then 1.4 to come down. So the way I'm doing it is the what I said before. I'm going to use the timeless equation using only the initial values, the final, because the final values are referring to after it lands. So we plug in this number and we end up getting the maximum height is 9.8 meters. All right. Here's the last one. Pause the video, work stuff. I'm going to go in a second. All right. Once again, we they give us all this information. They give us the speed and the angle. So what we're going to do is we do 7 sine 30, 7 cosine 30 to figure out what the x and y values are. The one thing to keep in mind is this. They tell us that the jump is 4 meters wide, but you notice that when I make my chart, that 4 meters does not appear because this 4 meters is what we call a reference number. It's just being used to kind of compare to our answer to see whether or not the person makes it. So what I'm going to end up doing is whatever I get for X, I'm then going to compare it to the 4 meters to see, well, if it's less than 4, he doesn't make it. If it's greater than 4, he does make it. So just keep that in mind that not every number they give you gets put into these charts or it gets used because sometimes numbers are reference numbers. But the way I set it up looks like this. Because of the fact that the second building is 1 meter below, what I did was I said that the first initial position is 1 meter up in the air and that the second building is actually at 0. Uh, but besides that, it's pretty straightforward. We want to figure out what this final position is, so I need to find the time first. So I'm going to use the y column, use the annoying equation, plug in numbers to find that the time it takes for it to land is 0.92 seconds based off this information. Then we use the annoying x equation, plug the numbers in, and we end up getting 5.58 meters. So does he end up making it across? Yes, because this number is greater than the 4 meters. All right, and that's it. We'll leave the other questions for later on in class. If you have any questions, feel free to let me know. Otherwise, good luck. Have a great day.